Hi, welcome to Lesson 13b, Lines in Two-Dimensional and Three-Dimensional Space. The goal of today's lesson is to learn how to determine and work with equations of lines in 2 dimensions and 3 dimensions. So to start off, let's look at something that we call a speed, distance, time triangle, where we have the distance, we've got the speed, and we've got the time. And there's the triangle. If we want to determine what the speed is, we cover up the speed and we divide distance by time. If we want to determine the distance, we cover that up and we multiply speed times time. So what we're going to do here is I'm going to start out by saying, well, let's look at velocity in 1 dimension. And velocity, sort of like speed except with direction involved, the velocity is x divided by t. So x is some distance moved over some generic time, or some specific time that we're looking at. I can rearrange this, so this is the formula to determine velocity. I can rearrange this and I can solve for the distance by multiplying both sides by t. So I multiply t on both sides, I would get then x equals velocity multiplied by t. And then if I want to find the final displacement from some given point of reference, given that the motion began some distance x naught from the point of reference, I can then add this in here. So this x then is going to be the final displacement, and that's going to be equal to the initial displacement from the given point of reference plus the distance that is moved when we multiply velocity times time. So that's the displacement along the x-axis. Then we can generalize this and say, okay, well, if all this is true for the motion in the x direction, we can do the same thing for the y direction. And we just say all of this again, but in for a distance, displacement along the y-axis. Then, knowing that now we can say, well, this velocity is going to be in the x direction, so I'm going to put a little subscript x here. And this velocity is in the y direction, so I'm going to put a little subscript y there. And t is the parameter. We can just set t to be any value we wish, and if we know x naught and v sub x, or y naught and v sub y, we can then find the position, the final position of the particle or the object we're thinking of by substituting in the value of t that we're looking for. So the velocity is in the direction of motion, therefore the velocity in the direction of motion is going to be vx, vy. So it's going to be a vector, v sub x and v sub y. Okay, that is called the direction vector for this line. Since we're looking at the displacement in the x direction and the displacement in the y direction, when we combine these two together, we end up mapping out a line as we increase in time, and the velocity is this direction vector v sub x and v sub y. That actually gives us the actual direction that the particle is moving. Okay, so these are actually called parametric equations, and what we're going to have, actually they can be simplified. The v sub x and v sub y are usually written just with single variables, so usually it's written as at and y would be y naught plus bt. So xy that's the position vector of any general point on the line, and that's the point that we can find by substituting in values of t. The x naught, y naught is a specific, the position vector of a specific point. So it's actually a vector, as is the, sorry about all that, jeez. So this is the general point, or the position vector of the general point on the line xy. This is the position vector of a specific point x naught, y naught on the line, and AB is the direction vector of the line. So that gives us the direction it's going in terms of how many units in the x direction, followed by how many units in the y direction. And then of course t is the parameter. Okay, so we can just set t to be whatever value we want, and then we can find out specific values of x and y along the line. If we put these two parametric equations together, as we've done here, this now is called the vector equation of the line. So what we've now formed is the vector equation of the line, and we can sometimes then see actually the a and b written. The textbook would write the vector equation like this. X, or actually not x naught, y naught, sorry. They write it as, sorry about that, falling apart here, a1, a2 as the components of the position vector of the specific point of the line, plus t multiplied by b1, b2. And these are the components of the direction vector. Another way of looking at it is vector r equals vector a plus t times vector b. And this is the position vector. Again, position vector. I am very sorry about all that. Jeez, I don't know what I'm doing here. The position vector of a point on the line, and the b is the direction vector of a point on the line, or of the line itself, sorry. If we then change this vector equation into the parametric equations, we just isolate things. We get x equals a1 plus b1t, and y equals a2 plus b2t. We can isolate t in both of these equations. So in this case, we're just going to subtract a1 from both sides here. So we get x minus a1, and then that would be x minus a1 equals b1 times t. We divide both sides by b1, so we get over b1, and that equals t. But if I do the same thing here, we get y minus a2 over b2, and that also equals t. So we can write it like that, or we can just eliminate the t itself, because they both equal t, they both equal each other. Okay, and this is what's called the symmetric equation of the line. Okay, so quick recap. We have the parametric equations of the line. In this form, we put them together, we get the vector equation of the line in this form, or also seen like this. And then if we take each of these parametric equations and we isolate for t, we get, and solve for, equate them, then we get the symmetric equation of the line, in this case here. Okay, so we're going to now do something with this. If we take that symmetric equation